Hi everyone! We have another effect on the agenda whose code fits on a single line. This time it will be a simple edge detection, which we can also use as an original way to fade out a scene, for example after finishing a level in our game. So let's go ahead and program that one line. So let's follow the usual pattern and create a new scene with the usual image in the background, that is a screenshot from our game Whispers of Prague. Let's do all the preparatory work. So I am right-clicking the scene folder, create a new scene. It should be a 2D scene, of course, and let's call it simple edge, for instance. Okay, and then I'll drag the usual image. It should be right here, found in JPEG, into the scene. So the sprite 2D node was automatically created, and in the inspector, let's do the usual stuff. In the offset, let's cancel centered, and in the transform, reset the position to 0, 0. Very well, and of course, scrolling down to the materials section, creating a new shader material. Let's click it, and in the shader, we'll create a new shader, type shader, mode canvas item, and the name would be the same as the scene, simple page.gd shader, and I'll put it to the shaders folder. Create and click again to open it in the shader editor. Let's expand that a little bit. And as always, I'll delete everything from the generated code so we won't need that we won't need for our effect, leaving only the fragment function. Deleting vertex, deleting white, and Control S to save. Great, we can start writing code. As I said at the beginning of the video, it will be a single line inside the fragment function. So I'll write its basic version first, and then we'll keep improving it. So I'll delete this comment and write this color equals function texture applied on our texture with the standard UV coordinates. Of course, we don't see any change because edge detection, let's just zoom out a little bit, because edge detection requires an additional calculation. This isn't the first time we've dealt here with an algorithm based on the difference of color values of neighboring pixels. As you may know, the Godot shading language includes the functions dfdx and dfdy, which make this calculation much easier because they return exactly what we need for edge detection. I've used them in previous tutorials, some of them, but this time we'll simplify things even further by taking advantage of a shorthand notation that combines these partial derivatives. This is the fwidth function, which also comes from the GLSL specification on which the Godot shading language is based. And as we can see, the fwidth function returns the sum of the absolute values of the dfdx and dfdy functions. So, how can we apply this function? Using it directly on the output of the texture function isn't ideal, because the result we get is an image where all pixels are transparent. Let's see, so I'll just apply fwidth on everything we can see here. And yes, so what causes this? The fwidth function computes the color difference across all color components of the pixels, including the alpha channel. And since in our image all pixels are opaque, their alpha components have a value of 1, so their difference will always be 0, which corresponds to full transparency. So let's try setting the alpha channel of the resulting pixel to 1. Color.a is 1. All right, I'll just show a bigger image. Now we have something observable. It's essentially a color representation of color differences Okay, that's a horrible phrase, but you know what I mean. The greater the difference between neighboring pixels, the more the resulting pixel approaches white. I can see, for example, in this lantern or in this fountain. Okay. But that's not exactly what we wanted to achieve, and our code has grown to 2 lines. So we'll make a small adjustment and subtract the value of the fwidth function from the original image pixel. It's very simple. Let's just add minus sign. Excellent. And now we no longer need the second line, so I'll delete it. And we are back to the 1-line shader. Of course, this is a very rough algorithm that probably won't produce ideal results in all cases, but since we want to use just a single line of code, this will suffice for now. So how can we improve it further? At the beginning of the video, we could see the image gradually darkening, which we can achieve by multiplying this function by a progressively increasing number. So let's add a uniform parameter and call it power. Let's put it here to the top. So uniform float power with a hint range, and the initial value we can set to, for instance, to 2, and it goes from 0 to, let's say, 10 with the step point 0, 1. Okay, and I'll use it in the code. So here I will multiply the result by the power value. Okay, it's a bit darker because we are multiplying it by 2. And when I change the value of the parameter in the inspector, let's do it here, we can see how it goes brighter or darker, because the multiplication increases the value being subtracted in the areas with the greatest color changes between neighboring pixels. Okay, so what else could we try? The fwidth function returns a vector. So what if we subtract its length instead? Which means we will wrap the length function around that. Okay, the results looks quite different because this time we are subtracting a number, a result of the length function, from the vector color. That means we subtract the same value from all components of the color vector, including the alpha channel, which causes the detected edges to gradually become transparent. Let's just try to change the power value, and we can see how it impacts the image. Okay, so if we displayed something else underneath our image, we could use this to create a new type of a transition between scenes. In fact, we can try it right away by adding a second image to the scene so that it appears first. Okay, and I usually use this one called chapel.jpg, so let's drag it to the scene. And, sorry, again. No, let's drag it here to the editor and do the same things. Reset channel, reset channel centered, reset position, and move it in the node hierarchy to the first place. And here we can see the result. Okay, and let's select the fountain object again, so we have access to shader parameters. Where are they? Here, and we can see how the transition works. Okay, I'm not sure whether something like this has practical use in a game. Maybe if the protagonists of the game were under the influence of psychotropic substances and started experimenting hallucinations. But who knows, perhaps you'll find a useful application, even if it means expanding the algorithm to more lines. Of course, you can experiment with anything. Thank you very much for watching. This time we were finished quite quickly, mainly because writing the code took very little time and I filled the rest by explaining various elements of the shading language. We'll see whether next time I manage to create something a bit more complex, perhaps even from a different category. And as always, I'll add a new shader to the Godot Shader Pack product, linked in the video description. For now, take care, good luck with your projects, and see you in the next video.